Have you ever seen one of those Russian dolls where you have like a doll, and inside the doll is another doll, and so forth? Well, I have a penny inside of my hand. I don't know if you can see it's a penny. And it's inside my hand, and inside that hand is another hand. Well, this is what we'd call nested. This is a nested penny right now, but we're going to look at what's called nested functions. This is climb time, and today we'll look at the derivative of what I call nested functions, but what most people call function composition. So derivative of nested functions or function composition looks something like this. We have two functions. We have a function here g and a function here f. And the idea is that our overall function h of x is a function within a function. That's how I say it. Because when you look at it, you can see that this function looks like it's inside of the function f. But when you look at the boxes, g doesn't look like it's inside of f. But when you look at the parentheses notation, it kind of looks like g is inside of f. What's actually happening is this. We have an input called x, and that x is the input going into the g function. The g function does something to it, and it puts out an output. That output is called g of x, and that's what comes out of the function. And that output, g of x, becomes the input for f. And so what comes out of f is f of g of x. So this is f of g of x. So the proper way to say it is we'd say f of g of x. And this is a function we're defining as h of x. So h of x is a composition of functions. It takes the output of one function and makes it the input of another function. I like to call it a function within a function because that's what it kind of looks like to me. All right, so the question is, how do we take the derivative if we have a function within the function? How do we take the derivative of h of x? What does that look like? So what I'm going to do is I'm going to look at a general example first. I'm going to look at a specific example first, and then we're going to go from there. So let's assume h of x is equal to the sine of 2x. Okay, so this is a specific example where we have one function, 2x, that's inside of another function, sine of input. So the overall function is h of x, and it has an outside, what I call an outside function, which is sine, and an inside function, which is 2x. All right, well, let's redefine this a little bit here. And let's say that 2x is our internal function, g. So I'm going to rewrite it to look like this. I'm going to say h of g is equal to the sine of g, okay? Where g is going to be like my internal function. So off to the side here somewhere, I'm going to say, I guess I'll just do it right here. I'm going to say g of x is equal to 2x. Okay, so g of x is my first function. It really is the first function. And then my input is x. And then what g does to it is it multiplies it by 2. So the output is just 2 times whatever the input is. That's what g is. So this is a composition of functions where you have, again, I'll just use my terminology, whether it's completely accurate or not, I don't think really matters. Where the outside function is sine of input and the inside function is 2x. So g of x is 2x, outside function is sine of input. So whatever the input is, I'm going to take the sine of it. All right, so how do I take the derivative? Well, we know how to take the derivative of this. So I can say h prime of g, which, by the way, there's another way to write that, which is dh over dg. Okay, that's going to equal the derivative of sine, and the derivative of sine is cosine. So we got the cosine of g, and we know how to do that. We have done that before. We've taken the derivative of trig functions. We know the derivative of sine of some input is cosine of that same input. Now up here with g of x, we can find the derivative of that. G prime of x, this is what I call the inside function, is going to be the same thing as dg over dx. And the derivative of 2x, we know how to do that. It's just going to be the slope of the tangent line. And because this is a line with slope 2, the derivative is 2. So dg over dx is 2. dh or dg is cosine of g. But what we want to find overall is we want to find h prime of x. So what is h prime of x? So I think I'm going to give myself a little bit more space here. So h prime of x, the derivative of the original function, h of x, well, that's going to be dh over dx. So how do we get dh over dx? And the answer to that question is we have to multiply both sides by dg. So we get dg over here, and then we have to divide both sides by dx. So if I multiply both sides by dg, I get dg. I'm sorry, we multiply both sides. Let me erase that. Multiply both sides by dg, we get dh on the left is equal to cosine of g dg. Okay, all I did was multiply both sides by dg. So that gives me dh. So then if I divide both sides of the equation by dx, I get dh over dx on the left, and on the right, I get cosine of g times dg over dx. All right, now I have something to work with. So what I'm looking for is dh over dx. And what I have on the right side are things I know. I know what g is 2x. I know what dg over dx, it's 2. So h prime of x, my overall derivative, is going to be this. It's going to be cosine of g, and cosine of g is 2x. So cosine of 2x, so I'm going to put that in, cosine of 2x. And then multiplied by dg over dx, which is 2. So times 2. And that is, in fact, the derivative right there. The derivative is of sine of 2x is cosine of 2x times 2. Now, what we end up with here is a process I went through that is true for any situation where you have a function within another function. So if you have a composition of functions where the input of one function is itself a function, if you get any situation like that where the input of one function is itself a function, I call that nested functions or a function within a function. Technically, it's a function composition. But if you have that situation, this is always what the result will be. It'll always be the derivative of the outside times the derivative of the inside. The derivative of the outside, the derivative of sine, is cosine. The derivative of the inside is 2. So 2 times the cosine of 2x is what the derivative would be. And that is called the chain rule. So let's generalize that. I'll use a new color for this one. So let's say we have a situation where we have a function within a function. So we have f of g of x. Okay, so the input of one function is itself a function. If you get that situation, the derivative will always be the derivative of the outer function, as I call it, times the derivative of the inner function. Okay, so this is the outer, this is the inner. So I'll go ahead and write that in, outer, inner. And that's how you find the derivative of a function within a function, or a composition of functions. And there's a name for this, it's called the chain rule. And the chain rule says that if you have a function within another function, to find the derivative, you find the derivative of the outside, and you multiply it by the derivative of the inside. And when I say outside, I mean the last function in the order. When I say derivative of the inside, I mean the first function or the previous function. There could be 3 functions that are composed. You could have a function within a function within a function. So if that were the case, you just sort of keep working your way down from the outside. So the last function is the outer function. The one right before it would be the inner function. And if when you go to find the derivative of the one right before it, if there's another function before it, then you got to apply the chain rule a second time. So you might have to keep applying the chain rule depending on how many functions you have nested together. So that depends on the situation there. But you can see here, there's nothing in this work that has anything to do with 2x or sine, aside from when we took the derivative side and the cosine. But the process is always going to be the same. You're always going to have an internal function. The internal function will always be defined as dg over dx. You'll have an outer function. The outer function would always be defined as dh over dg. And so the process here that stays the same is we multiply both sides by dg, and we divide both sides by dx. So you'll always have the derivative of the outer function here and the derivative of the internal function here. So that is called the chain rule. And so that's what you do when you have a function within a function.